So let's take a look at this example problem. I'm going to go through and show you my hand solution to this problem, give you an idea of my train of thought as I'm going through these, how I break things down, and analyze the problem. So we take a look at the problem. The first thing we want to do is just read through the entire problem statement, make sure we understand what they're giving us and what they're asking us to solve for. So read through this here. We have a cantilever beam deflection model. So in this problem here, the deflection of a cantilever beam is the distance its end moves in response to a force applied to the end as shown down here in this figure. The distance is called the deflection and it is the output variable. The applied force is going to be our input. The following table down here gives the measured deflection x that was produced in a particular beam by the given applied force F. So we have our force and deflection here in this table. They want us to plot the data to see whether a linear relation exists between F and X. So the first thing that I like to do with any of these word problems is to kind of break it down, read through everything that's given in there, and really get a grasp of what they're telling us for information, the knowns, and what they're asking us to find. And I like this format here where I write down a whole section where I explicitly write out what's given in that problem statement. And I also write down here, okay, I'm going to separate out what are they asking me to solve for. For the more long involved problems, this is really nice because we may forget exactly what we're solving for the end of the problem. So we can always reference back to this slide here or this page in our solution here to understand, okay, this is what they're asking me to solve for. So as I read through that problem statement, understand, okay, they give me the weight. We're labeling this as F, and it's in units of pounds. So I have the description of what's given, the variable that they're using, and the units. And here we have now deflection, they also tell us. That's X, and that's going to be given in inches. If we take a look here at this chart that they give us here, we have force in pounds, and we have deflection in X. So we have for 0 pounds, there's 0 deflection. For 100 pounds, there's 0.15 deflection, so on and so forth, all the way up to a load of 800 pounds and a deflection of 0.77. Now, what are they asking us to solve for? They want us to plot the data to see whether a linear relation exists between our F and our X, our force and our deflection. I also like to redraw out the diagram, the given diagram. And sometimes it helps to simplify it down for some of the more complicated diagrams they give us. So this is the first thing that I like to do with any problem that I'm solving, is to go through and break things down. What do they give me? What am I looking for in any given diagrams? So let's take a look at this example problem. I'm going to go through and show you my hand solution to this problem, give you an idea of my train of thought as I'm going through these, how I break things down, and analyze the problem. So we take a look at the problem. The first thing we want to do is just read through the entire problem statement, make sure we understand what they're giving us and what they're asking us to solve for. So read through this here. We have a cantilever beam deflection model. So in this problem here, the deflection of a cantilever beam is the distance its end moves in response to a force applied to the end as shown down here in this figure. The distance is called the deflection and it is the output variable. The applied force is going to be our input. The following table down here gives the measured deflection x that was produced in a particular beam by the given applied force F. So we have our force and deflection here in this table. They want us to plot the data to see whether a linear relation exists between F and X. So most of the time when you're doing your homework problems, you're going to be writing these solutions out by hand. So even though I just went through and showed how to type out our givens, our find, what we're looking to solve for, and all the known information of the problem, I want to go through and do my hand solution for this as well. So in this problem here, I've gone through and I've written out, okay, this is the title of my problem. It's example problem 1.3.1, so I know exactly what problem I'm referencing to. What do they give me in the problem statement? So I read through that problem statement from the problem for 1.3.1, and I realize, okay, they give me my weight as F in units of pounds, and this is a force. And they give me my distance as a variable X, units of inches, and this is our deflection as related to our problem here. Now I redraw out a simplified version of our given diagram right here. So what I have here now is a cantilever beam problem. So this beam has some weight, which we're calling here our F, and apply a force at the end of the beam. Now, we're measuring this with a dial gauge according to our diagram here, and for each force that we apply to this here, we have a corresponding deflection or distance, x. Now, this information for how the deflection corresponds with the applied load is given to us in this graph down here, or this chart here. So again, we have force at 0, deflection 0. So we can tell right there, if we're not applying any force, we have 0 deflection. If we apply 100, and then we have units of pounds here, I can reference back, 100 pounds, I get a deflection in inches of 0.15, all the way through up to a load, applied load of 800 pounds, and this has a deflection of 0.77 inches. So I have all the given information now written out here so I can reference back to it. I like to keep this all on the first page so I can easily reference back and understand what everything is, know what's given to me, and know what I'm solving for. So that leads us to what are we solving for? In the problem statement, they tell us, plot the data to see whether a linear relation exists between our f and x. So this is my first page, this is what I'm solving for, this is my given information, this is my given data set, and this is my given diagram. So now the next step will be to solve the problem. So we need to come up with a solution. So now that I have my first setup page all done, I know where my givens are, I know what they're asking me to solve for, I have my diagram, I have my table chart. I can always reference back to that as I'm going through the solution of the problem. So the next step is that, the solution. We need to take a look at all that given information on the first page and now come up with a solution for this here. So for this solution, one thing I know is that there is 0 beam deflection if there is no applied force. So that's from the given data and the given problem statement. We can make that assumption there. So that lets us know that the curve must pass through the origin. And that's going to simplify down our solution as we do this hand plot. So down here, I've done out my hand plot, and this is a real rough hand plot here. It's kind of a demonstration of why I prefer to plot things either in MATLAB or Excel. If we are going to do a hand plot, some line engineering or grid paper would be ideal, or at least a ruler to measure things out. So what I have here now is I have my two axes here. On the bottom x-axis, I have my applied force, F, units of pounds. And on my y-axis over here, I have my deflection, x, in units of inches. So I come across here and I have my 0, 0, so I know my line is going to start here. I have 100, 200, 300, all the way up to 800, and 0.1 all the way up to 0.8 on my x-axis. So now I can reference back to that chart on the first page. So again, this is another great reason to have that first page separate there. I can look at my chart from that data and start putting in, okay, at 100 I know this, at 200 I know it's this x value, at 300 I know it's this x value. Plug these all in, so now you can get your deflection for each of these applied f's, and then you can plot all of these on this graph here, and then what I've done is drawn a linear approximation from my first known point here all the way up here through my lines here. Now there's a couple different ways that you can do this. This is just a quick straight line approximation using a ruler, starting at my axis here and following up roughly through the center of all my data points. So again, this is rather subjective due to the fact that this is all done by hand. So a numerical plot is going to be a lot more accurate. So if we're using something like MATLAB or Excel, that's going to be a lot more accurate for getting our straight line linear approximation, for getting our slope of the line, or anything else that we may need from that. We can back the data out a lot easier and a lot more accurate. But even this data here plotted by hand does show that this straight line does lay close to our data. So our data is very close to the straight line approximation here. So we can use a linear function, x is equal to AF, in order to describe our relation. So the value can be determined from the slope of this line here. So now that I've shown my hand plot for this data here, the next thing I want to do is show you one of the other options. For something this simple, I prefer to use Excel rather than MATLAB. It's a lot quicker to get some data results from something this straightforward. If this is a more complicated problem, I may choose to plot this in MATLAB. We're going to get a little bit more into MATLAB plots and functions as we move on throughout the semester. For this one here, I just created two columns within Excel here. I have my force in pounds, my deflections in inches. I simply type in those values from that given information in the problem statement from the table that they gave us. And then what I can do is I can come up here, depending on your version of MATLAB, or I'm sorry, of Excel that you're using, go to Insert here, Plot it, whatever type of data you want to do. I've already done this, so I can go over to my chart here, and I've plotted this out. Now with this plot here, you can see this is almost identical to what I did by hand for my hand plot here, where I have my data points, where I have my applied force in pounds across the bottom, my deflection in inches on the y-axis up here, and you can see I plotted these as a scatter plot, so I have the individual dots for the data points all the way through. Then what I did was you can right-click on these guys and add a trend line. So that's what I've done there is I've right-clicked on these and I've added a trend line here, and then when the trend line options pop up over here on the right, I selected linear. And I've kind of proved this to myself by looking at the data from my hand plot there, a quick and dirty rough hand plot. So I said, yeah, that's close enough. My data points are pretty close to a straight line, so I'm going to pick linear here. And with this one here, I can also do two other things in my data set. One, I can set that intercept here for 0. So now we can go through our origin point down here at 0, 0, which is exactly what we want to do from the problem statement there, because when there's 0 applied load, there's 0 deflection. And then the other thing I can do is I can display the equation on the chart. And what this does here is this will actually calculate the slope of this line there. So you can see this is 0.001x, so y equals mx plus b, where b is our intercept is 0. We set it to 0 there, so y equals mx, where m is the slope, so there's my slope right there.